Hello students, I am Vandana. In my last classes, I explained definition of a sequence and some more definitions based on sequences. From this class onwards, we will discuss about important theorems and some more definitions. To learn all these things, you must and should watch my previous videos, then it will become more easy to understand. Okay? First in this class, I want to explain about limit of a sequence and convergent sequence. This definition is useful for uniqueness theorem. Okay, see here, limit of a sequence first. Limit of a sequence. For this we need to consider a sequence first. I am considering here sequence S and be any sequence and L belongs to R. L belongs to R is said to be L be any real number. Then we can see that L is a limit of a sequence. When we will say that L is a limit of a sequence, if it satisfies one condition. What is that condition? See here, if I reach epsilon greater than 0, epsilon, see this is the epsilon greater than 0. Epsilon is nothing but very least positive integer. There exists m belongs to n. M belongs to n is nothing but m be any natural number, such that mod Sn minus L less than epsilon for all n greater than or equals to m. Mod value is always positive. So to say L is a limit of a sequence, it should satisfy this type of condition. Okay. Also we can say that sequence Sn is converges to L. Okay. Here, what is the definition? L is the limit of a sequence. What about the sequence? Sequence is said to be converges to L. From this we can write, if the sequence has a limit L, suppose sequence Sn has a limit L, then we can write Sn converges to L as in n tends to infinity. This is a representation for convergent. Okay, Sn converges to L as n tends to infinity. Or we can also write like this, limit Sn n tends to infinity is equals to L. Okay, if Sn converges to L as n tends to infinity, or we can write like this also, limit Sn n tends to infinity is equals to L. Or simply we can write limit Sn is equals to L. Okay, this is a definition of limit of a sequence. Next definition, convergent. Convergent sequence. Convergent sequence. For this also we need to consider a sequence. So a sequence Sn is said to be convergent. When we say that a sequence is convergent, if it satisfies this condition, see here, if there exists L be any real number, such that for each epsilon greater than 0, there exists m belongs to z plus. M belongs to z plus, m belongs to m. Same, right? Positive integers. A z plus is also running from 1 to infinity, and a natural number system also running from 1 to infinity, such that mod Sn minus L less than epsilon for all n greater than or equals to n. Same condition, right? The only change is here we concluded L is a limit of a sequence. What we concluded here, sequence Sn is convergent. That is the only difference. Okay? Note point. See here, limit Sn is equals to L if and only if sequence Sn is equals to sequence Sn is convergent. From these two definitions we can conclude it like this, right? Limit Sn is equals to L. If you have this condition, you can use this condition. Similarly, if you have this condition, you can use this condition. Okay? If you want to prove sequence is convergent, we can consider limit value, and finally we need to prove that that limit should be equal to 1L. Then we can write sequence Sn is convergent. Okay? Next, also we know that limit n tends to infinity 1 by n is equals to 0. Limit 1 by n value 0. Next, similarly limit n tends to infinity 1 by n power p is equals to 0. Okay, next, uniqueness of a limit. This is very important theorem for 5 marks. I thought they may ask state and prove uniqueness of a limit. So you should write a statement also. A convergent sequence has unique limit. This is our statement. Sometimes they may ask like this also. A sequence can have at most one limit. See here, what is our statement? A convergent sequence has unique limit. So for this we need to consider a convergent sequence first. Then we need to prove it has unique limit. Unique limit is nothing but it has only one limit. I am considering here Let L and L dash be two limit points of sequence Sn. Why I am considering two limit points? Why? Because we need to prove uniqueness, right? So I am considering two limit points. Finally, we need to prove those two limit points should be equal. Okay. Suppose L not equal to L dash. We need to prove L equal to L dash. But I am considering here L not equal to L dash. Why? Because I am solving this problem in contradiction way. If we get a contradiction, then we can write L equal to L dash. Okay. So suppose L not equal to L dash. From this we can write mod L minus L dash greater than 0. Clearly, mod always positive. So we can write mod L minus L dash greater than 0. Take epsilon is equals to 1 by 2 mod L minus L dash. Epsilon is nothing but very least positive integer. Positive. Already mod value positive. If we divide it by 2, then we get again a positive value. That should be least. So I am considering epsilon is nothing but 1 by 2 into mod L minus L dash. Okay, clear? Next I am considering, since L and L dash are two limit points of a sequence Sn. So L is a limit point of a sequence. L is a limit point of a convergent sequence. Sequence Sn is convergent. So L is a limit point of convergent sequence Sn. L dash is also a limit point of convergent sequence Sn. So we can write, since sequence Sn is converges to L. From this, okay, converges to L. By the definition of convergent, we can write for each epsilon greater than 0, there exists m1 belongs to Z plus such that mod Sn minus L less than epsilon for all n greater than or equals to m1. Okay, m1 is a positive integer. Also, sequence Sn is converges to L dash. We have two limit points, right? First, sequence Sn is converges to one limit point, that is L. Next, sequence Sn is converges to another limit point, L dash. So again, by the definition of convergent, we can write for each epsilon greater than 0, there exists m2 belongs to Z plus such that mod Sn minus L dash less than epsilon for all n greater than or equals to m2. This is a condition by using convergent. Okay. Here n greater than or equals to m1. Also n greater than or equals to m2. So we can write, if I am consider m is equals to maximum of m1 and m2, then we can write mod Sn minus L less than epsilon for all n greater than or equals to m. M is a maximum of m1 and m2. So in place of m1 we can write m. Similarly, mod Sn minus L dash less than epsilon for all n greater than or equals to m. Again, n greater than or equals to m2. Same, m is a maximum of m1 and m2. So in place of m2 we can write m. Clear? Next, see here. Consider mod L minus L dash. Subtract and add Sn. Since we know that mod A plus B is always less than or equals to mod A plus mod B. From this we can write less than or equals to, consider this as A, this as B. So from this we can write mod L minus Sn plus mod Sn minus L dash. Okay. Since we have mod Sn minus L less than epsilon for all n greater than or equals to m, mod Sn minus L dash less than epsilon for all n greater than or equals to m. What do you have here? Mod Sn minus L dash. But here we have L minus Sn. So take minus common. So from this we have Sn minus L. We have no problem. Why? Because what we have here, mod. So mod minus negative values became positive. Mod Sn minus L dash. Mod Sn minus L always less than epsilon. Mod Sn minus L dash always less than epsilon for all n greater than or equals to m, which is equals to epsilon plus epsilon, 2 epsilon. Starting we considered mod L minus L dash. What is our inequality here? Less than 2 epsilon for all n greater than or equals to m. Since what is the value of epsilon? What I am considered here? 1 by 2 mod L minus L dash. This is nothing but 2 epsilon mod L minus L dash. Okay, so we can substitute mod L minus L dash in place of 2 epsilon. So that implies mod L minus L dash less than mod L minus L dash. Is 2 less than 2? Is 2 less than 2? So similarly, is mod L minus L dash less than mod L minus L dash? No, right? So which is a contradiction. Why we get this contradiction? Since L not equal to L dash, so our supposition wrong. This is our supposition, right? So our supposition was wrong. If our supposition wrong, L not equal to L dash, this is our supposition. This is not existed. If it does not exist, then the only chance is L equal to L dash. L and L dash are limit points. L equal to L dash. So both limit points are equal. From this we can write sequence Sn has unique limit. Sequence Sn has unique limit. Therefore, every convergent sequence Sn is nothing but convergent sequence. So every convergent sequence has unique limit. Hence proved. Okay, this is a uniqueness theorem of a limit. Next class we will discuss some more important theorems. Do like, share and subscribe my channel. Thank you.